Hello students, welcome to the class of complex analysis. So we are discussing the section zeros of analytic function. So next theorem says that let G be a connected open set. Suppose we have a complex plane and G be a connected open set. Connected open plus open. Okay. Then I defined an analytic function f from G to C, the complex plane. Okay. Then we need to prove that the following three statements are equivalent. First statement says that f is identically equal to 0. So that means f maps every element in G to 0. Okay, all elements are mapped to 0. Second statement says that there is a point A in G. There is a point A in G such that when you consider f dash of A, f double dash of A, since the function is analytic, we can find out all the derivatives because it is infinitely differentiable, right? So f dash of A, f double dash of A, etc., f nth derivative of A, etc. are, these all are maps to 0. Right? Okay. And the third statement says that if you consider the inverse image of 0, that means f inverse of singleton set 0, which means you consider all the elements which are mapped to 0. So that set, that means f inverse of 0 set is or it has a limit point in G. We need to prove that this set has a limit point in G. So these are the three statements given in the theorem. We need to prove that these three are equivalent. That means there is some connection between these statements. Okay. So first we will prove 1 implies 2. 1 implies 2. So let the function f is identically equal to 0 in G. Okay. So if when a function is identically equal to 0 means f z is equal to 0 for every z in G. So which implies f dash z is equal to 0 for every z in G. Then which implies f double dash of z equal to 0 for every z in G. So continuing this manner, we get every derivative of z equal to 0 for every z in G. That means for any point in G, it's any derivative of the function f at the point z is equal to 0. Right? So all the points at which the f nth derivative of that point will be equal to 0. So which implies the second statement will be true. Second statement is there is one point and I can say that every points have this property. So which implies there exist point A in G such that f nth derivative of A equal to 0 for every n greater than or equal to 0. So we can prove that 1 implies 2 very easily. Okay. And we will prove that 1 implies 3. 1 implies 3. So assume 1. 1 implies 3. Okay. Assume 1. Assume f is identically 0 again. When a function is identically equal to 0, okay, then we have to prove that the set of all z in G such that f z is equal to 0 has a limit point in G. Okay. So when a function is identically 0, I can write f z equal to 0 for every z in G. Okay. So what is the inverse image? Consider the set z. Consider the set of all z in G such that f z is equal to 0. And this set is nothing but f inverse of the singleton set 0. Since the function f is analytic, it is continuous also. Right? Therefore, and you see what is a singleton set 0? Singleton set 0 is a closed and compact set in complex plane. Right? Singleton set 0 is a closed and compact set in C. Then inverse image will be a closed set. Inverse image will be a closed set. Right? So that I can say this set contains its limit points. So which implies f inverse of 0 is a closed set, contains limit points. And what is f inverse of 0? F inverse of 0 is set of all points at which maps into 0. So you can see that f z is equal to 0 for every z in G. So this is nothing but G. So which implies it has a limit point in G. Set of all z in G such that f z is equal to 0 has limit point in G. Limit point in G. Okay. Okay. Now we will prove that 3 implies 2. 3 implies 2. So that is, if this set has a limit point in G, we will prove that there is a point A such that this derivative equal to 0 for every n greater than or equal to 0. Okay. 3 implies 2. So for proving 3 implies 2, assume set of all Z in G such that Fz is equal to 0 has a limit point in G. Okay. Now I define this set is equal to some capital Z. Okay. Okay. Then by your assumptions, the set Z has a limit point in G. Okay. Now let A be a point, actually limit point. Let A be a limit point of Z in G. So I consider a limit point of Z in G. Okay. Now we will claim that at this point fnth derivative of A equal to 0 for every derivative n greater than or equal to 0. We need to prove that there is a point in G such that the required property, and we will claim this point has that required property. Okay, this is our claim. So by proving this, I consider if it is not happen, what will? If it is not true. If it is not true, that means fnth derivative of A is not equal to 0 for every n greater than or equal to 0. So if it is not true means fnth derivative of A is not equal to 0 for some n. For some n. That means there is some derivative of that function at that point A, that derivative not equal to 0. Okay. So we have this. Now, since A is a limit point, of Z, I can consider a sequence in Z which is converges to A, which implies there exists a sequence Zn in Z such that the sequence Zn converges to A in G, because A is an element in G, right? Therefore, we know that function f is analytic, right? When a function is analytic, that will be continuous. Since f is analytic, comma, f is continuous. Okay. Therefore, we can apply this function for this convergence. So, which implies f of Zn converges to f of A. Converges to f of A. Okay. And what is f of A? And this therefore this f of A can be written limit n tends to infinity f of Zn, because it converges to A means limit of this sequence will be equal to f of A. So that is equal to limit n tends to infinity. What is f of Zn? Zn's are elements in capital Z, right? Zn is a sequence in capital Z. Therefore, Zn's are elements in capital Z. Therefore, this Zn has the property of capital Z. So, when Zn belongs to capital Z, Zn is an element in G and f of Zn must be equal to 0, right? Therefore, this instead of f of Zn, I will write it is 0 because Zn is an element in Z. Therefore, f of Zn must be equal to 0. So, limit of 0 is 0. So, you get f of A equal to 0, right? Okay. Now, we have A is an element in G. What is G? G is open set. Comma G is open. Implies there exists some R greater than 0 such that BAR is contained in G. Why? Because when G is open, elements in G will be an interior point. When it is an interior point, there will be an open disk which is completely contained in G with the center A for some radius R. So BAR will be contained in G എന്ന് നമുക്ക് കിട്ടും. Okay. And since again by analyticity, since F is analytic in G, analytic in G implies F is analytic in this open disk, analytic in BAR. Therefore, F has a power series expansion on this open ball, right? Therefore, Fz can be written sigma n equal to 0 to infinity an into z minus a raised to n for mod z minus a less than r, and this r is the radius r. Okay, where what is an? Where an is defined by fnth derivative of a divided by n factorial. Okay, but what is fnth derivative of a? We know that fnth derivative of a not equal to 0 for some n. Only for one n this is non-zero. All other derivative at that point will be equal to 0. Okay, so which implies you consider such an n, choose such an n. Here I will write choose n such that fnth derivative of a is non-zero and f1 f dash of a 0, f double dash of a 0, etc. f n minus 1th derivative at that point equal to 0. Choose such an n. Okay, so then you can find out this a naught will be 0, a1 will be 0, a2 will be 0, etc. a n minus 1 will be equal to 0. Right, all these terms will be 0. Therefore, fz can be rewritten as sigma n equal to, since a1, a2, etc., a naught, a1, a2, etc., a n minus 1, 0, we can omit that terms. So, this summation will be starting from some, I can write k equal to n to infinity. Okay, ak z minus a raised to k. Because up to nth term, these an's are 0, so it is starting from an only. Okay, now we define a function. Now define a function g of z is equal to sigma k equal to n to infinity. Okay, ak z minus a raised to k minus n. Or then gz can be rewritten as z minus a raised to minus n into sigma k equal to n to infinity ak z minus a raised to k. So which is equal to z minus a raised to minus n into 1. What is this? This will be actually here I can write 0 to infinity, right? 0 to infinity. So this will be nothing but fz. So gz can be written z minus a raised to minus n into fz. Therefore, right. Then we can say g is analytic because we have fz is an analytic function, right? Since f is analytic in g, therefore it will be analytic in b of a comma r, right, in that region, that is mod z minus a less than r. Okay, then you consider z minus a raised to minus n, that is 1 by z minus a raised to n, right? So what is this region b of a comma r, which is a open pole centered with a and radius r, right? Therefore 1 by z minus a is a non-zero number, right? Therefore its power is also non-zero, which is non-zero in the region mod denominator is non-zero in the region mod z minus a less than r, that is bar. Therefore in this region this function is also analytic. So by using analyticity of f and this function, because it is the product of two analytic function, implies gz is analytic in bar. And what is using gz, I can also write fz is equal to z minus a raised to n into gz. Like gz is equal to z minus a raised to minus n into fz. Therefore fz is equal to gz into this can be written here z minus a raised to n. Okay. Now we have gz can also written, what is gz? Gz is equal to actually an plus 1 into z minus a. We substitute these values. Okay, k equal to n to infinity. So an z minus a raised to n minus n, that is 0. So ak into z minus a raised to 0, an into z minus a raised to 0, that is an. And you take the next term n plus 1, we substitute k for n plus 1, we get an plus 1 z minus a raised to 1 plus an minus 2 into z minus a square plus etc. Okay, then what is g of a? G of a equal to, when you take a, these all terms will be 0, so you get an. And we have an is a term which is non-zero term. Why? Because an is defined by f nth derivative divided by n factorial, and we have assumed that f dash of a equal to 0, f double dash of a equal to 0, etc. f n minus 1th derivative at the point equal to 0, but f n the derivative at a not equal to 0. So by using that term, that condition, this an will be nth derivative divided by n factorial at that point. Since it is non-zero, the term will be non-zero. Therefore, g of a is a term non-zero. Right. So which implies g is analytic in BAR, in the region of BAR, and g of a is non-zero. So analyticity always implies continuity. Right? Analyticity always implies continuity. Therefore, g is continuous in BAR, open ball centered with the A and radius R, and g of a not equal to 0. And g of a not equal to 0. So which implies if there is a continuous function and for one point it is non-zero, means there will exist a neighborhood. In that neighborhood, that function will be non-zero. അല്ലേ? ഒരിക്കലും ഒരു കണ്ടിന്യൂസ് ഫംഗ്ഷൻ എന്താ പറയുക, സീറോയിൽ നിന്ന് നോൺ സീറോയിലേക്ക് സഡനായിട്ട് പോകാൻ കഴിയില്ല. അതിന് നമുക്ക് കണ്ടിന്യൂസ് ആയിട്ട് മാത്രമേ പോകാൻ കഴിയുള്ളൂ. അപ്പോൾ ഏതെങ്കിലും ഒരു കണ്ടിന്യൂസ് ഫംഗ്ഷൻ ഒരു പോയിന്റിൽ നോൺ സീറോ ആണെങ്കിൽ തീർച്ചയായിട്ടും there will exist one neighborhood, at least one neighborhood such that that continuous function attains non-zero values on that neighborhood. Okay, so which implies there exists a neighborhood u of a such that u of that point a, this point a, such that gz will be non-zero for all elements z in u. So which implies gz is non-zero and u is a neighborhood of a. And we have assumed that since a is a limit point of the set Z, by our assumption, what is a? A was the limit point of the set Z. Z equal to set of all Z in E such that fz is equal to 0. Okay. Then by the definition of limit point, if a point is a limit point of a set, then every neighborhood of that point will intersect with that set, right? Therefore, u intersection Z will be non-empty. Which implies there exists an element B in that intersection u intersection Z such that B not equal to A. നമുക്കറിയാം ഡെഫിനിഷൻ പ്രകാരം ലിമിറ്റ് പോയിന്റ് ആണെങ്കിൽ അത് അല്ലാത്തൊരു പോയിന്റിലായിരിക്കണം ഇൻ്റർസെക്ഷൻ. ദാറ്റ് സെൻറ്റർ പോയിന്റ് അല്ലാതെ മറ്റൊരു പോയിന്റിലാണ് ഇൻ്റർസെക്ഷൻ ചെയ്യേണ്ടത്. സോ ദർ ഈസ് എ പോയിന്റ് ബി ഇൻ യു ഇൻ്റർസെക്ഷൻ സെറ്റ് സച്ച് ദാറ്റ് ബി നോട്ട് ഈക്വൽ ടു എ. Okay, so which implies B belongs to U and B belongs to Z. So what is the meaning of that? B is an element in U and B in Z. So B is an element in the neighborhood of A and B belongs to set of all Z in G such that fz is equal to 0. So which implies B is an element in U and f of B equal to 0. B is an element in U and f of B equal to 0. Okay. Then you consider g of b. You consider gz equal to by definition this. Then g of b will be equal to b minus a raised to minus n into f of b. But we have f of b equal to 0. Therefore, we get g of b equal to 0. Right? G of b equal to 0. So which implies the function g is 0 in neighborhood of u at the point b. Which implies g of z equal to 0 in the neighborhood u, in a neighborhood u of a at the point z equal to b. Right? Is it possible? No, because g is a function which is continuous and which is non-zero at the point u. So we can't take then u is a neighborhood of that point a in which g is non-zero. We have g of a is non-zero. Therefore, we found a neighborhood u of a. A neighborhood and u such that g of z is non-zero in u ആയിരുന്നു. Now we get a point in that neighborhood u such that gz equal to 0. So which is a contradiction? Which is a contradiction to this idea. Therefore, this condition, therefore, our assumption was wrong. Therefore, our assumption was wrong. Therefore, g of z is therefore fnth derivative at the point A is 0 for every n greater than or equal to 0. There is no derivative at which f with that derivative point A is non-zero. So we proved C implies, so we proved 3 implies 2. Now for the last equivalence, we will prove 2 implies 1. Okay, the last statement 2 implies 1. Okay, so for that assume that the condition 2, the statement 2, assume that there is a point A in G such that fnth derivative at that point A is equal to 0 for every n greater than or equal to 0. Okay, we want to prove that f is identically equal to 0. Our claim is f is identically equal to 0 in G. Okay. So for that, I define a set first. So let capital A equal to set of all z in G such that fnth derivative at that point z equal to 0 for every n greater than or equal to 0. That means we are considering such A's, this kind of A's. Fnth derivative of A is not 0 for every n greater than or equal to 0. Clearly, this then this set will be non-empty because A is an element belongs to this set, right? Since element A is always belongs to capital A. Okay. Now we will claim that this capital A is a set which is a Kloppen set. That means which is both open and closed. A is a Kloppen set. Kloppen means both closed and open. So we are going to prove that A is a closed set as well as it is an open set. So to prove A is closed, we have to prove that A contains all of its limit points. So I consider a limit point of A. So let C be a limit point of A. So we need to prove that C is an element of A. Right? When you have a limit point of a set, then we can consider a sequence, which implies there exists a sequence Zn in A, in that set, such that the sequence Zn converges to C as n tends to infinity. Okay. Now, since f is analytic, we know that every analytic function has the property that it is infinitely differentiable. That means all of its derivatives are again differentiable or analytic. So which implies for every m greater than or equal to 0, fnth derivative at the point set, fmth derivative of that function will be analytic or differentiable. Analytic. So which implies fmth derivative will be continuous. Because all differentiable functions are continuous. So fmth derivative is a function which is a continuous function. Then we can apply this continuity to this sequence of convergence. So which implies fmth derivative of the sequence Zn will be converges to fmth derivative at the point C. Okay. So which implies f of C can be written, fmth derivative of C can be written limit n tends to infinity fmth derivative of Zn. So which is limit m tends to infinity. What is fmth derivative of Zn? Zn is an element in capital A. And A is set of all z such that fnth derivative of z is equal to 0. Right? Therefore, when Zn belongs to this collection, its derivative at that point Zn will be 0. So this is equal to 0. So you get fmth derivative at the point C equal to 0. So when fmth derivative of at the point C equal to 0 for every m greater than or equal to 0 means C is a point in A. C is a point in A. So which implies when you have a sequence in A and which is converges to C and C is also belongs to A means C is a limit point of A and it also belongs to A. Which implies A contains all of its limit points. Therefore, A is closed. A is a closed set. Now we are going to prove that A is an open set also. So to prove A is open, we have to prove that Yeah, the every points are interior points. So I take a point, let A is an element in capital A. When A is an element in capital A belongs to G because A is a subset of G. Okay. So when A is an element in G, A is an interior point of G because G is open. A is an interior point of G since G is open. Open set contains all points are limit points. So which implies when G is open, there exists a radius r greater than 0 such that an open ball centered with A and radius r is completely contained in G. Okay. Then we have f is an analytic function. Okay. When we have an analytic function which is analytic in G implies which is analytic in BAR also. Which implies f is analytic in BAR by using the analyticity of function in G. So then we can find a power series representation, right? So which implies f set can be written a power series representation sigma n equal to 0 to infinity a n into z minus a raised to n for z in this region, that is mod z minus a less than r, where a n is equal to f nth derivative of a divided by n factorial. But we have the element A, small a is an element in capital A. Therefore, this element has the property that f nth derivative of A equal to 0 for every n greater r equal to 0. Therefore, these ANs are equal to 0 for every n. When all ANs are 0, the coefficients are 0, then the power series becomes 0. Therefore, the power series representation of that function is also equal to 0. Right? And this will be to 0 for every z in is belongs to BAR. Open ball with the A, center and radius r. So which implies f z is equal to 0 for every z in A means what z is an element in capital A. Z is an element in capital A. When f z is equal to 0 means f dash z will be equal to 0, f double dash of z will be equal to 0, etc. All the derivatives become 0. So z is an element in capital A. So when you take an element in BAR, then when you take an element z in BAR, because z satisfies this condition when z is an element in BAR. When z is in BAR, we get f z has all derivatives as 0. Therefore, z is an element in capital A. So, BAR is an open ball centered with the A and radius r is completely contained in A. So, which implies A is a interior point of capital A. Since A is arbitrary, capital A is open. Since A is arbitrary point of capital A. So we proved that capital A is a set which is both closed and open. Therefore, which is a open set. So which implies capital A equal to set of all z in G such that f nth derivative of z is equal to 0 for every n greater or equal to 0. This set is a non-empty open set in G. And what is G? G is a subset of complex number. We know that complex number is also a topological space, right? By using the metric topology. Okay, so in a topological space, a set is connected if and only if there exists non-empty open subsets. So here A is a non-empty open subset of G. So which implies A must be equal to G because G is a connected set. ഒരു കണക്റ്റഡ് സെറ്റിൻ്റെ ഉള്ളിൽ നോൺ എം ടി ആയിട്ടുള്ള മറ്റൊരു ക്ലോപ്പൺ സെറ്റ് കാണാനായിട്ട് കഴിയില്ല. അഥവാ അതിനകത്ത് ഇഫ് ജി ഈസ് എ കണക്റ്റഡ് സെറ്റ് ആൻഡ് ജി കണ്ടെയ്ൻസ് എ നോൺ എം ടി ക്ലോപ്പൺ സെറ്റ്, then that set must be equal to G because no connected set can contain non-empty open set by topological axioms. So A will be equal to G. What is A? Set of all z in G such that f nth derivative z equal to 0 for every n greater than or equal to 0. So which implies that for every z in G also has this property f nth derivative of z equal to 0 for every n greater or equal to 0. So when all derivatives are equal to 0, we can prove that f is identically equal to 0.